All right, AP Chemistry, this is the assignment answers video for day 28, lesson 13 on empirical formulae. So watch the video first and go ahead and do this along with the video or after the video. All right, so we're going to compute some empirical formulas, very much the same as was done in the video. First question is, what is an empirical formula? So an empirical formula is okay, so it is the lowest whole number ratio of atoms in a chemical compound. And what is an empirical formula used for? Okay, so it's an intermediate step between obtaining measurements in the lab and what you ultimately want to know, which is determining the actual molecular formula of the compound. All right, so let's go ahead and do this. So the first question, compute the empirical formula for the following HO compound. So in doing the lab, you can decompose this HO compound into hydrogen and oxygen. And you can know that you have hydrogen and oxygen and how much in grams through laboratory techniques. So the first thing you have to do is anything involving a chemical compound subscripts or a chemical reaction has to be in moles, not grams. So we have to go ahead and compute how many moles of hydrogen we have. If we have, let's read this, in the decomposition of this compound produces 0.857 grams of hydrogen and 6.86 grams of oxygen. What is the empirical formula? Okay, so let's go ahead and figure out how many moles of hydrogen that is. And from your periodic table, you know this relationship. 1 mole of hydrogen for every 1.01 grams of hydrogen. Do the same for oxygen. All right, so we obtained 0.849 moles of hydrogen and 4.429 moles of oxygen. Now the next step is create a ratio of the number of moles of each element that you obtained and place the smallest number of moles on the bottom. So the smallest number of moles here is the 0.429. So hydrogen, this gives us 1.98, which we're going to round to 2. It's close enough. If it's within about 0.05, it's okay to round to the nearest whole number. And of course, this one gives us exactly 1. The element with the smallest number of moles is always going to end up with a ratio of 1. Okay? So part 3 says divide the top number by the bottom number and place the quotient above a 1. Okay? So we did that. We actually did that. So, well, we do it here. So it's going to be H is on top. So we divide this by this, and we already have it placed over a 1. So it's a 2-to-1 ratio is what we're saying right there. There's 2 hydrogen for every 1 oxygen. Multiply the top and bottom of the fraction by whole number until you have a whole number on the top and bottom. Well, we already have a whole number on the top and bottom, so we don't need to do that. But if this was 2.5, for example, that's not close enough to either 2 or 3 to round it. So you would multiply that by 2 and you would get 5. Then you'd also have to multiply this by 2 and you'd get 2, so you'd have 5 over 2. But that's not the case here. You already have a whole number, so it's good. So we've got that same ratio. All right, and we'll move on to the next page. And now it is saying, finally, to finish the problem, place these numbers as subscripts of the elements, this is the empirical formula. So the empirical formula for this compound is H2O, 2 hydrogens for every oxygen. And of course we all know that's water, but we don't know at this point whether that's the actual molecular formula for this molecule. All we know at this point is that there's 2 hydrogens for every 1 oxygen. Alright, so let's go ahead and work another one here. This time we have nitrogen and oxygen. So it says in a decomposition reaction, this compound produces 24.5 grams of nitrogen and 70 grams of oxygen. What is the empirical formula? So we're going to compute the number of moles. Not a lot of space here. I'll have to do this like this. This is from the periodic table. It's going to give us, okay, one here for oxygen. Okay, so we have 1.81 moles of nitrogen and 4.375 moles of oxygen. Next, we're going to create a ratio of these numbers with the smallest number, which is 1.81 on the bottom. And that's going to give us 2.41. Let's just call it 2.4. We're going to call that 2.4. Okay, so we have a ratio of 2.4 oxygen atoms for every 1 nitrogen atom. So we could write that as NO 2.4. 1 nitrogen for 2.4 oxygen. It's a decimal point. But you're not allowed to have a decimal number there. All right? You've got to have a whole number. So what we're going to have to do is a series of multiplications until you get a whole number there. Okay? So we're going to start, we'll just put the O up on top here. And that's 2.4. And nitrogen is 1. So if you multiply this by 2, that equals 4.8. We'll leave this alone until we're done. Okay, that doesn't get us to a whole number. That's not close enough to round. So we're going to multiply it by 3. So 3 times 2.4, that gives us 7.2. That's not close enough to 7 to call it a whole number. So we're going to go to 4. And you multiply that, that gives you 9.6. That's clearly not close enough to either 9 or 10. I'm going to come down here, I'm going to do 5. And that equals 12, exactly 12. Okay, so we're going to have to multiply this by, we're going to have to multiply 2.4 by 5 to get 12. That means we have to multiply the nitrogen by 5. So these are the two that got us to whole numbers. And of course, that any number times 1 would have given us a whole number. So this was the one that was the issue. We had to get that oxygen to be a whole number. So we have N5 and O12. That's the lowest whole number ratio. You can't reduce 5 over 12. So the formula is going to be N5O12. All right. And that's how you find the empirical formula of that. Okay, now we're going to compute the empirical formula of a compound that has 3 elements in it. CHO, that could be some kind of carbohydrate, could be a vitamin of some sort. Oftentimes it's something that you will eat or consume. All right, so the decomposition reaction of this compound produces 60 grams of carbon, 4.48 grams of hydrogen, and 35.52 grams of oxygen. What is the empirical formula? All right, so let's go ahead and figure out the molar mass, number of moles using molar mass conversions. Okay, we get 4.99, so we're going to call that 5. Okay, we go on to hydrogen. Okay, and that gives us 4.44. And I'll come up here and do oxygen. And that gives us 2.22. 2.22 moles of oxygen. Alright, so here we go. So we have 5 here, 4.44 here, and 2.22 here. Now we create 3 ratios. 2.22 is the smallest of these 3 numbers, so it goes on the bottom. Hydrogen is 4.44 over 2.22, and that's going to equal exactly 2. And then oxygen, being the one with the smallest number of moles, is going to simply be a 1. Okay, so here's the numbers we're interested in. Okay. And actually, I should have done that down here, divide the top number by the bottom number. Okay, so I have these 3 numbers right here. This one is not a whole number. So I can forget about these 2 for a second. Let's figure out what I have to multiply this by to get it to be a whole number. So let's just do it in sequence. So 2 times 2.25 equals 4.5. That's not a whole number, not close enough to round. So let's go to 3. You just sequence all the way up until you hit 1. If you're good enough to just look at it and tell you, then you're good to go. Okay, that's going to be 7.75. That is not close enough to round to 8. Okay, so let's try 4. And that equals 9. So that is a whole number, so we're good to stop. So that means we have to multiply everything by 4. This is the number we have to multiply by. So we get 2.25 times 4. So for carbon, let's go ahead and just do that again. Hydrogen had a 2 there, so it's going to be 2 times 4. Everything just has to be scaled up by 4. And oxygen was a 1. So these are going to be your subscripts, 9, 8, and 4. Okay, so we'll go ahead and write that right here. It's going to be C9, H8, O4. So that is the empirical formula. Now we're going to take it one step further. It says if the molar mass of the compound is 361.51, what is the molecular formula? Okay, so let's run that one. So we have a formula that this factor that we're going to multiply these subscripts by is equal to the molar mass over the molar mass of the empirical formula. So it's the molar mass of this. Well, that's not a quick and easy one to do in your head, so let's write it down. Let's do it like we did it back a week ago when we were doing molar masses. So we have carbon. There are 9 of those times 12.01 grams per mole. And that is going to give you 108.09. Hydrogen There are 8 of those from your periodic table 1.01. And oxygen, there are 4 of those. It's 16 for each oxygen. That equals 64. Okay, and we can put 0.00 because on the periodic table it's 16.00. So now you simply add those together. And it gives us 180.17. Put this on screen a little better. Okay, and that's grams per mole. That's for the empirical formula. So we take the molar mass, this number, do it down here, 361.51, divided by the empirical molar mass that we just calculated, 180.17. Do the math on that, and that gives us virtually exactly 2, so let's call it 2. So that's our factor N. So that's what we're going to multiply these subscripts by to get the actual formula for the actual molecule. All right, so let's just do that here. 2 times 9 is 18. 2 times 8 is 16. And 2 times 4 is 8. And that is the actual molecular formula, the actual formula of the actual molecule. All right, and that's how you do those problems. Okay, so we're going to wrap up. We're going to do a couple of the combustion reaction of hydrocarbons that you saw in the instruction video. These are exactly the same, it's just the numbers are different. All right, so let's go ahead and do these. But first we're going to calculate the molar mass. This is how many grams of carbon dioxide we obtained from the chemical reaction. We weighed it. We saw we had 5.72. Same thing with water. We had 1.17. So these actually are the same numbers as in one of the problems there. So go ahead and see if you can do this on your own. You saw it in the video. See if you can do this. So first thing, you just got to make this a reflex. Whenever you see grams and you're dealing with a chemical equation, you've got to compute the mole. Okay, so I've computed the number of moles of CO2 and H2O. Now I could have written this all as one big long equation, but I'm breaking it up for instructional purposes. So let's start with CO2. We know that for every mole of CO2, let's just start with molecule. With every molecule of CO2, you need 1 atom of carbon. So for every mole of molecules of CO2, you need 1 mole of carbon. So it's a 1-to-1 relationship. So I can now take this number, I'll come down here. Okay, so I have 0.13 moles of carbon. So that's how much carbon I have in the CO2 that I measured. All of that carbon had to come from this carbon. There's nowhere else you don't have any other carbons over here in the reactants. So it had to come from there. So if I have 0.13 moles carbon there, I have to have 0.13 moles carbon over here. Okay, so carbon is taken care of. Now we can do the same with oxygen. With hydrogen. Okay, so I'm going to take this one. Actually, I'm going to take the moles of H2O here. And we can see that for every mole of water we have to have 2 moles of hydrogen. We have to have twice as many hydrogen atoms as we have water molecules. Okay, each bicycle takes 2 wheels, so you need twice as many wheels as you have bicycles. So that ratio here is going to be and moles of H2O cancels with moles of H2. I should have done that here too. Moles of CO2 cancels with moles of CO2. Last man standing. Last man standing is going to be moles of hydrogen. And 2 times 0.065 is going to give us 0.13 moles of hydrogen. Okay, so we have 0.13 moles of carbon, 0.13 moles of hydrogen. All right, so that means over here we have 0.13. And that means all of the hydrogen you see there had to come from this CH compound. So that means over here, I'll write it up above, same thing. Okay, so we figured out that we have a ratio now of 1.3. So now we can write the empirical formula C.13 H 0.13. But of course you can't have decimals in subscripts like that. They have to be whole number ratios. So just create a ratio out of these two numbers. And of course you get 1 to 1. So that's the CH compound, C1H1, which of course you just write as CH. And I'm off screen. Here we go. Okay, so we just took the 0.13s, put them as subscripts. You can't have that, so you make a ratio. They become 1 to 1, so you get CH for that. Okay, so there's that. I'm not asking you to do the molecular formula. If I would have to give you, think about what would you need? You would need the molar mass of that unknown gas, of that CH compound gas. If I gave you that, you could then use the ratio, figure out the factor, and what you had to multiply those by. Okay, let's go ahead and do it. I didn't ask you to do it. So, if I gave you what I gave you in the video was molar mass. Of 78.11, I hope I'm remembering that right, grams. That's the molar mass of the unknown gas. The empirical molar mass is going to be, you got 1 carbon, so carbon, let's just go ahead and calculate it, is 1 times 12.01, they get that off the periodic table, equals 12.01. And for hydrogen, again, this is not a real molecule. Well, maybe it is, but at this point you don't think it is. But you're just computing the molar mass of that empirical formula. And there's 1 hydrogen, that's 1 times 1.01. And that equals 13.02. So the formula is, the factor is molar mass and that's going to be 78.11 over 13.02. Do that on your calculator, and I'm just going to approximate it. You get approximately 6. So you're going to take the 1 there and the 1 there and multiply that by 6. So this is the empirical formula here. So that's actually what the problem was asking you for. And the molecular formula is going to be these numbers multiplied by 6. Okay, that's just for show and tell. That wasn't actually asked in the problem. And that molecule is called benzene. Okay, let's keep going. One more. And this time I won't do the whole molecular. Let's just go ahead and do this one. See what you come up with. Just do the empirical formula here, okay? So try to do it on your own. You know the steps. You got to get grams to moles. Okay, so now we have moles of each. So now we're going to calculate how many moles of carbon and hydrogen we have. So we're going to bring this one down here. And there's 1 mole of carbon for every 1 mole of carbon dioxide. Two moles of hydrogen for every 1 mole of water. Okay, now we're going to make our ratios. The smallest number, these are our two numbers of moles. The smallest number is 0.27 for I'm sorry, 0.24. It's 0.24 moles for carbon. We're comparing carbon to hydrogen here. It's 0.24 moles. So hydrogen is going to be and carbon is the smaller of the two. Again, ignore that. Carbon's the smaller of the two. So that's going to have a ratio of 1. Okay, so we have 2.25 there. So we don't have a whole number there, so we're going to have to multiply. And we already did this one, actually. So for hydrogen, let's just walk through the sequence. 1.2, so 2 times 2.25. That's not a whole number. That's not a whole number. That's a whole number. So that means we have to multiply the carbon by 4 as well. Okay. Alright, so we have a 9 and a 4. 9 for hydrogen, 4 for carbon. So our empirical formula is C4H9. And that takes care of that. Alright, so that's how you do empirical formulas. It's about, think about this, it's only about 5 steps. It doesn't, you're going to have to practice 5 steps, but it's not impossible to learn 5 steps. Probably you just try to learn 1 step for each time you do a problem, and by the end of doing 5 problems, you've got the 5 steps down. Okay? So that takes care of that, and limiting reactants is our last subject in the this unit. All right, we'll see you then.